So now let's see how we can do the loading and storing of information controlled in the register. The first approach that we will consider is called the clock gating. What we do with the clock gating is that instead of providing the clock directly to the flip-flops clock input, you use the OR gate and introduce another input, which is the load input, and then the output of the OR gate will be applied to the clock input of the flip-flops. You can see what we have as the clock input of the flip-flops. It's not load or clock. So as you can see, while the load is equal to 0, then C input will remain as 1, and therefore there will be no rising edge of the clock, and that's what you could see over here in this region. On the other hand, if the load is equal to 1, then the C input will be equal to the clock itself, and that's what happens in this segment. When the clock is equal to 1, then the C input is equal to the clock, and therefore these rising edges that we have for the clock will appear at the C input as well, and therefore the register could be loaded. So we can say that when load is equal to 0, register stores the information, while load is equal to 1, register updates its content. So that's one way of doing it. But another way, which is more reliable in terms of the timing, let's see, because with the previous case, with the clock gating, there might be some timing problems depending on when the load becomes true and when we have the rising edge of the clock and for how long the load remains 1. Things like this may create some timing issues. The next approach, which doesn't depend on the clock gating, is using basically the multiplexers. In this case, the clock will be provided to the inputs of the flip-flops directly, so they will receive the same clock as the rest of the system, but the input to the flip-flops will be controlled. We will determine whether to pass the new data, D0, D1 that you see here, into the input of the flip-flops, or whether to pass the current value that we have for the flip-flops to the input of the to their input in it. Yeah? It is done using the AND gates, OR gate, and one inverter for each flip-flop. You can see here, and you can also see that each combination that we have here works as a 2-to-1 line multiplexer. With the load signal, we select the input. There are two inputs. One is coming here, which is Q0. The other input is D0 to our multiplexer. So with load, we choose among this. If load is equal to 0, Q0 will be selected. With load equal to 0, then D will be equal to Q0, and therefore it will store the old information. But while load is equal to 1, D will be equal to D0, and the flip-flop and the register will be loaded. And that's what we have for the second case as well. So load equal to 1 loads the information, load equal to 0 stores or keeps the old information. You can see that compared to the previous approach, the hardware is more complex, but it doesn't have any timing problems. So whenever load is equal to 1 and there is the rising edge of the clock, the flip-flops will be loaded with the new data, and otherwise it will hold its old data.